All right, so let's get started. So let me introduce Professor Gael Richard. He's a full professor in audio signal processing at Telecom Paris. He received a PhD from University of Paris-Saclay in 2001. He's the scientific co-director of the Paris Interdisciplinary Center on AI and Data Analytics for Society. He's a co-author of over 250 papers, an inventor of 10 patents. In 2020, he received the grand prize of IMT National Academy of Science for his research and contribution to sciences and technologies. He's a fellow, he's an IEEE fellow, and he was a past chair of IEEE Signal Processing Society, Technical Committee for Audio and Acoustic Signal Processing. Today he will present basically an approach on interpretable AI for audio. We are really honored and privileged to have Professor Gael Richard with us today. And without further ado, I leave the floor to Gael.
Okay, thank you very much, Cem, for this very nice introduction. So I'm very happy to be here today. So in fact, I'm going to talk about some approaches towards explainable and interpretable deep audio processing based on hybrid deep learning, and I will spend a few times to explain what I mean by hybrid deep learning. So here's the content of my talk. After a short context and motivation introduction, I will go towards hybrid deep learning, give some other examples in various domains, focus a bit on hybrid deep audio learning, and then focus on several application examples, and especially on audio synthesis example, taking as examples papers that will be presented during the week in ICASP. Okay, so machine learning, as all you know, there is a growing trend towards pure data-driven, and of course it leads to high performance, but as you know, we have main limitation there, is that the knowledge is only learned from data, that it leads often towards very complex models with billions, if not more, numbers of parameters. It basically operates in overconsumption regime in terms of complexity, but also on energy consumption. And also what is of interest here is that it's mostly non-interpretable and non-controllable. So this was at the heart of my ERC project, High Audio, where the main goal is to build controllable and interpretable audio machines, which can be frugal. And basically, it is done through the concept of hybrid deep learning, basically by integrating our prior knowledge about the nature of the processed data. So, of course, this is not new. And in fact, in physics, it's also a very active domain where they have very strong models of physical model about what is going on for predicting, for example, climate or climate aspects. For example, here it's an example with predicting the temperature of a lake. And then they exploit their models and they exploit, deep neural network to help to import data and to treat data at the same level, within this physical model. And this leads towards what they call physics-guided neural networks, which is typically a hybrid deep neural network. And also, more recently, there were some work in other domains, in digital communication, image communication, and a very nice paper by Schlesinger and colleagues, and around describing the different ways you could do a model-based deep learning or hybrid deep learning. And to go a bit further on that, we have, for example, two paths. One is going from using more and more domain knowledge, and one is going to use more and more data. And of course, if you go from the left to the right, you go more from the pure data-driven to the pure model-based domain, and you have a bunch of possibilities to build hybrid deep learning models where it's hybridizing the two conceptual approach. So I recommend this paper, which is quite clear about the different possibilities to mix the two approaches. So of course, in audio, it has a major interest, and I'm going to describe a bit more how we can do a similar concept in audio. And of course, some of them have already been presented by Ehsan a bit earlier today. So basically, we would like to go towards hybrid deep learning. So if I extrapolate the concept of the physics-guided neural network, we can use models, which are typical for describing knowledge about audio, and replace the physics-based model by these typical models that captures audio knowledge. So these typical models for audio can be perceptual models because we know how audio is perceived, can be signal models because we know how audio is structured, can be physics-based model, Einstein physics, but they can also be musical models because we know we have some prior knowledge about what is music. And then we can hybridize this with the deep neural networks and build these so-called hybrid deep learning models. If I focus a bit more on music, it can be expressed in a slightly different way. So we have these potential signal models, physical models, which in this sense will be physical models of the instruments, can be musical models, what is structure in music, what is beat information, how music is composed, and perceptual models. And it can be inputted or help or used, I will say, in different aspects, either to curate or to annotate the databases, either as input representation, either directly in the hybrid in the deep neural network at multiple stages, or can be, for example, one way to do it is to integrate the model as constraints in the loss functions. Okay, so one easy way to do a first easy way to exploit signal models, for example, is to use decomposition models, such as based on the non-negative matrix factorization algorithm. So basically, this NMF, non-negative matrix factorization, tries to describe an input spectrogram that you have on the upper right as a figure. So it's frequency versus time, where it's a spectrogram of 3 notes. The first time the one note is played, then a second note is played, and then the 2 notes are played together. And this is decomposed into 2 matrices. One matrix which captures the spectral content, or the atoms, or which can then the different atoms, we build a dictionary. This is a matrix W. And the matrix H, which is the other matrix, will say at which point of time each of these template, which of these atoms is activated over time. And we can see that we have a very nice decomposition of the note in blue and the note red, which is the 2 notes are played at the end together after. So how can we use this non-negative matrix factorization? An easy way, for instance, is to use it as an input, an informed input representation. So we can then replace, for example, here is an example in audio scene classification. We can replace the input spectrogram representation by an NMF representation, where it describes the spectrogram as a sum of objects which are activated in time, and it can replace maybe by replacing the input representation, we can build a network which is quite smaller, basically reaching the same type of performance, but in a much less complex way with less layers. So this is one way of doing hybrid deep learning. In fact, it's not a very satisfactory way because it's only replacing the input. It's not really building a hybrid system where the knowledge is inputted at different layers or different levels of the deep neural network. So I mentioned NMF also because I know that Gael Richard is going to present a way to use NMF to do post hoc interpretation of deep neural network, which is another way of building, of using such interesting decomposition approach, which have been also very successful in audio source separation. Okay, so NMF can be also, it's one way of finding this W and H matrix is to rely on an iterative algorithm. And since it's iterative, it can be translated into, so we have an optimization algorithm to solve the problem, to find the 2 matrix W and H. And if you have an iterative algorithm to find the W and H matrices, you can translate this way of computing the matrix into a succession of operation done by layers of a deep neural network. So basically, here you will exploit a deep neural network architecture to express a signal processing algorithm, which exploit, of course, the knowledge about the audio. Another way of doing hybrid deep learning, which exploit also this idea of multiple iteration, is around the algorithm of Griffin and Lim, which is an algorithm which tries to find the phase spectrum from the knowledge of only the amplitude spectrum. Basically, you want to find the Fourier transform while you only have the amplitude spectrum, the spectrogram. And it's an iterative algorithm where you go back and forth by computing the Fourier transform, then going back to the time domain, going back to the Fourier domain, and so on. And gradually, you converge where a solution where you have an estimation of the phase, which is better than just assuming that it's random. So again, you can, since it's an iterative algorithm, you can also exploit this iteration within a deep neural network structure, where here is done in a way that it's the neural network is used to denoise each iteration of this Griffin and Lim operation. So you do one Griffin and Lim operation. It's a bit noisy. It's not perfect. Then the deep neural network will help to denoise this operation, but still keep this iterative way. So why it is interesting here? Because here it's also clearly combining deep neural network power to exploit data and the knowledge prior with the conceptual algorithm of Griffin and Lim. So I'm going to present a few additional work around this Griffin and Lim algorithm and how it can be used in other works. Okay, so now after this short introduction and some overview of some aspects of hybrid deep learning, I'm going to give a few examples with a focus on audio synthesis, sometimes music and sometimes general audio. So one example, which has been presented by Ethan this morning, is based on this so-called DDSP approach, where we couple deep neural network and signal processing model in a way that the deep neural network will learn parameters of a synthesizer. And when the parameters have been estimated, the synthesizer can synthesize sounds based on the parameters found by the deep neural network. So here you have a complete model, I will say, where you have an audio that you want to analyze and synthesized audio that you want to synthesize with the found parameters. And you have a deep neural network architecture, encoder and decoder, which will estimate the different parameters of this sum of harmonics plus noise model. You also have other aspects, which you can also find some parameters of reverberation. And for doing that, you optimize a so-called multi-scale spectral loss, which is basically comparing the spectrogram as multiple scales, and also in a linear scale or dB scale, and which is a way to compare a spectrogram and taking into account in a loosey manner the phase information, because you don't have the phase in the spectrogram. So one of the things we could also extrapolate from this, you can say, okay, the whole model is optimizing a multi-scale spectral loss, and which, as I mentioned, it's a way to take into account the phase, but in a way that is not really constrained and which is not really specified. It's just doing the comparison of the spectrogram at different scales with different window size. So one way is to say, okay, maybe we can think about a loss which relates more to physics or relates more to the phenomenon of the comparison we want to do. So and so this is at the heart of this study, which will be presented by Bernardo during this week in his poster session. And basically, when you do a multispectral loss, you compare the two content. So here it's a sum of sinusoids. So it's a synthetic example where you compare them as in a way that it can be called vertical, because you compare them on by comparing the representation as a scalar product, for instance. And when you do, you can do it differently. You can say, what can I do to change from one sound to the next? And this can be expressed in terms of optimal transport, where you try to move the energy from one sound to the next sound. And so then you can build a distance which is based on the spectral optimal transport concept, and hopefully have inserted principle of physics in the loss you want to use for this synthesizer. And in fact, it can be shown on synthetic example that this distance is quite smooth, and it has very good gradient orientation, and it's not as noisy when you compare it with multiscale spectral loss, where it's quite noisy on this example. And it's very good, but only when you are close to the minimum. So just to give a bit of explanation, but of course it will be further explained in the paper during this week. You can not only base a system on this new metric, but you can combine the two metrics. So for example, you have a sum of loss, one based on the spectral optimal transport, one based on the multiscale spectral loss, and you weight the two loss to build this new system and to find, as for the raw DDSP, the parameters of the synthesizer for representing the sound. And in fact, it was shown that on simple example, that it could improve the pitch estimation and the audio reconstruction using such metrics. Another example that I would like to describe is on still around this problem of phase estimation, or can be called also on the translation from spectrogram to waveform. In fact, if we look at recent text-to-speech systems, they often split the operation in two big steps. There is a first step which goes from text to log-mail spectrogram, and then a second step, which goes from log-mail spectrogram to waveform. And of course, you have systems that goes end-to-end, but so then I put a few names about the algorithm that go from text to log-mail spectrogram, and the one who goes from log-mail spectrogram to wave. But here I'm going to talk only about the task of sound generation from mail spectrogram. So going from log mail spectrogram to waveform. And you have a few algorithms to do that I'm going to briefly describe. And some of the examples are based on diffusion models, which are very interesting models where you can build a forward and a reverse process, where you can go from sampling to a noise domain and step by step generating the image. And if it's audio, step by step, you will generate the audio. And basically, this is interesting because you can sample in the noise domain, obtain in a forward process, and with the reverse process, you will generate sound, but you will have ways to control this this generation. So there is a quite nice example for speech, for example, for speech generation, which are called wavegrad and specgrad. I'm going to briefly describe these models. So basically, you start from the logged mail spectrogram, which are used as condition information. You sample in the noise domain, and gradually, by reversing the diffusion process, which denoise this noise, we'll say this noise spectrogram, you converge with the wave information conditioned by the log spectrogram. So I could play the sound, but I will not play the sound now, but it's a bunch of sound on the internet, but the quality is quite good, and I will say very good for retrieving the waveform only from the log spectrogram. There is also some let's say, improvement of this method, or that in fact, having only a sampling from the noise is a basic approach, and it's a basic algorithm, but there is no insight of what we are really doing. It could work for any types of data as soon as the model is trained with a specific type of data. But if we consider that we have a speech or audio, then we can use prior information. And for instance, saying that, okay, if we know that the spectrogram is going to follow some kind of energy with time, then we can imply this prior information directly in the noise. So then it will help a faster convergence for the synthesis aspect. And this is the idea that is beyond prior grad and spec grad, is that the noise is not only a Gaussian noise, is shaped noise, either shaped in energy, so it is more or less strong, or it can even be shaped by the variance of the signals in the spectral domain. So then if it can be pink noise, where you have more energy in the formant region of the speech. And in fact, by changing this prior based on the knowledge of the content of the speech, then it can help to further gain in terms of performance for this conversion log-based spectrogram to waveform. So one idea, which is can be also to go further, is to say, okay, we have a reverse process to go from noise to audio. We know that we are going from male spectrogram to waveform, and we know also that we have an algorithm, a signal processing algorithm, which is a Griffin and Lim, which help to go from the male to the spectrogram to the waveform by recomputing the phase. So we have this knowledge of what is phase in audio. So then we can integrate this Griffin and Lim algorithm within the diffusion process. So then when we do the diffusion process to go from noise to waveform, we integrate the knowledge that we want to have an audio signals, which has a spectrogram with a given magnitude spectrum and a well-estimated phase spectrum. And in fact, this is the idea behind this work, is to integrate the Griffin and Lim in the process to gain performance for that. So basically, it is done like that. We have this noise at one step. We do this Griffin and Lim correction, which is described in the lower box, before the next noise estimation step. And then by doing that, we have a better control of the different diffusion steps to go from yn to y0, which is a waveform. And again, this is going to be presented as a poster during this week by Tessir Baoubeb. Just to give a few hints about the result, we can see that it's one of the major outcomes of this result is that by incorporating these phase models, we have a stronger generalization performance to unseen speaker. We have integrated some knowledge, prior knowledge, and we gain generation performance, which I think it's a very nice outcome. And the cost is not. The cost to pay is not in terms of performance, it's more in terms of generation speed. It's a little bit slower than without using this Griffin and Lim algorithm. But there is quite a very good, let's say, good trade-off between quality and inference speed. Another example of exploiting a diffusion model in sound generation and in combining information in the prior information in the model is to go back to this model of SpecGrad, where you have prior information about spectrally shaped noise. So here it's the model is a little bit more complex, and I will invite you to go to check the poster. But one of the idea here of increasing importing some knowledge in the system, is to use spectrally shaped noise in a way that here there is a GAN system, and in a way to make the work of the GAN more challenging, and in controlling the challenge you want to put on the GAN's generator. And in fact, what is done here is to put more noise in low energy region. So the GANs is having more difficulty to operate, and we can control this difficulty by making it less and less difficult, for instance, to help the model to converge. But it's another way to have control on the system by exploiting knowledge about the content of the signal. Okay, so maybe I can skip these details, but I invite you to go to check the poster. Now I'm going to jump in a slightly different domain where we consider audio generation, but in text. So it's like symbolic music generation. So what is symbolic music? It's a description of music using score or a representation which describe score in a different manner, such as the MIDI representation or piano roll. And in fact, then the music can be represented as a sequence of tokens. So then, of course, we are close to the domain of text processing because it's a sequence of tokens. And what we can say that data-driven symbolic music generation is difficult, and you may lead into inconsistency in melody and rhythm, and you can also have many problems in generation because you don't take into account context and musical knowledge. So the idea is that how can we add knowledge about musical structure, for example, in data-driven models? So if, for example, if you work with transformers, you have, of course, this key concept, which is based on attention. And this key and the attention, what it does, it links attention from input variables towards output variables. But as a raw example, it has some invariance to temporal orders of the inputs. So this is one of the role of the positional encoding, is to provide some information about which element of the input sequence comes in which order. And in fact, you can go a little bit beyond that, not giving only the order of the input sequence, but to exploit some kind of musical information to describe what you should focus on from a musical aspect of the different input. So then it can go towards musical structure-informed positional encoding. So for instance, I give a few examples of what you could do there. If you do no positional encoding, then you only use the input. If you want to do absolute positional encoding, you will add an information which is the time of each of the input information. And then you can do structure absolute positional encoding, and also there are also potential variation, but where the information you add is not only the time ordering of the information, but it's information about tempo, phrase, chord, or pitch information. And so this is quite nice. And in fact, the results show that you can have better music generation if you use this knowledge in the positional encoding for music generation. And again, I invite you to check well, it's not a poster, it's a representation this afternoon by Manvi about the structure info positional encoding for music generation. Okay, so then going back to the using models for deep neural network and different tasks. So then I discuss a bit of a few applications on audio synthesis. Let me describe an application on unsupervised source separation, where in fact it will exploit audio synthesis, but within a model for source separation. So basically here you have the concept, you have the source separation. So from the input mixture, you will try to find the different sources But instead of building an algorithm which will filter or will unmask the source you want to discover, you will synthesize the different source, and you will only compute the distance between the synthesized mixture and the input mixture of sounds. So then it's a difficult problem because you have multiple source, but only one observation, which is a mixture of the audio. So to help the system, what you do, you will incorporate prior knowledge by means of source production model. So you will know the source about synthesizer, and you will have as many synthesizer as sources. And if you have good knowledge about which source you want to synthesize, you will help the model to do the separation. And what is interesting here is, in fact, it's completely unsupervised because you never need to learn the system with the separated sources. You will only learn the system with the mixture signals. So here in this case, the example I will give is for separating multiple sources which are the same, which are a singing voice. So singing voice, we know we have very good models of source production model for singing voice. In fact, can be based on the so-called source filter model, where the source represents the vibration of the vocal folds, and the filters represent the resonance of the vocal and nasal cavities. And of course, it is a new model because it's a new paradigm, because it's a source separation by synthesis. You will have no interfact in the different sources because it's done by synthesis, and learning only from the polyphonal music, which I already said. But also it can lead to novel sound transformation because it's largely explainable, because you can manipulate the different sources. You can do change of the melody, change of the timbre. You can change the lyrics. You can do translation. You can reharmonize, and you can do many things because you have a bunch of synthesizers which produce the different individual sources. And another advantage here is to separate homogeneous source, because it's the same type of source. It's 4 voices. So how does it work? This system, we have an estimation of the fundamental frequency of each of the source, which is done externally, not within the network. Then we have a kind of heuristic to assign each fundamental frequency to each source. And then the DNN will predict all the parameters of these differentiable generative source models, which are based on DDSP, which I will describe a bit further later. And the loss, which is optimized here, is the classic spectral, multispectral loss between the mixture and the synthesized mixture. So the parametric model is a bit complex. We have a very complete model for the source, which can characterize the harmonic content of the vocal source and the noise content of the source to be able to produce all types of speech sounds or all types of phonemes for singing voice. But it's basically a source filter model where there is an excitation source with all the parameters that are seen on the left, which are the source is synthesized and then filtered by the filter, which is an all-pole model, so only representing resonances, following the classical linear predictive model, where in this work, the coefficients are estimated by these line spectral frequencies, but it's really the same concept of estimating an all-pole models which characterize the resonances of the vocal tract. Just to give an idea of the architectures, all the blue, all the green dots are the part of the models which predict parameters of the model. So it's exactly the same concept of the DDSP. Here, the deep neural network predict models, predict parameters of the synthesizer, which are going to be used to synthesize the different sources. But here, the source, F0, the fundamental frequency, are estimated externally and not within the model. It's not a completely differentiable model. But what can be concluded from this study is that by doing unsupervised, we can show that it's as good as if we're training a supervised, almost as good. That there is almost no drop of performance when we use very few data, only 3% of the data, comparing the models where we train with 3% of the data or 100% of the data. And also there is much less drop in performance when we compare to models which are supervised, because in a supervised way, when we train with only 3% of the data, then the performance drops much faster. So what is interesting, if I may say a word again on that, is that we have gained explainability, we have gained controllability, we have gained generability, and we have not too much lose in performance compared to supervised approach and to approach which were, so compared to supervised approach and compared to approach which have no controllability. Also in a following work, and which I'm going to present also tomorrow afternoon in a poster, it has been extended to a fully differentiable model, where also this multi-fundamental estimator and this multi-fundamental estimator and assignment to each of the source is also made differentiable and integrated in the full model and fully optimized with the full model. So then it leads to a fully end-to-end unsupervised source separation models, and again with this explainable model at the heart. So of course there is a few problems in that approach, is that there is some aspects which are apparently non-differentiable, because you need to assign each source to assign each fundamental frequency to each source, and this is a non-differentiable based on a non-differentiable max operation. But a specific trick was done here in the spirit of this VQ VAE models to pass and to pass a gradient for the optimization. But again, I'm going to discuss a bit more this model tomorrow. What is the conclusion of this, or the outcome message of that, is that the end-to-end approach is a little bit less accurate than the baseline, than the semi-integrated approach, but it's much more robust on out-of-domain data. And in fact, it's because also that in the original model, the heuristic to do the assignment was done in a smart way, but in looking only on one type of data. And as soon as you were using out-of-domain data, this heuristic knowledge approach was too weak, where here you're exploiting multiple data and can leverage on this and finding an assignment method which is more robust to diverse data and new situation. Okay, so you have a number of demo signals for this approach, either on the on the semi-integrated approach and on the fully integrated, on the fully differentiable model. I don't know if I have time to play sound, but in any case, don't hesitate to check this web page, and you have a more liberty to listen to the different sounds and see what type of performance can be obtained from a fully unsupervised model. Okay, so then to conclude, I have, I hope I have illustrated what is the potential of this so-called concept of hybrid deep learning, that it can lead to more interpretability, controllability, and explainability. It's mostly here explainability by design, of course, because you build a system where you integrate the prior knowledge with a deep neural network. So it's by design, and if I take again the word of some of the talks this morning, is controllable by human understandable parameters, because it's simple synthesizer, for example, which are used. But it also brings new capabilities. This interpretability is not only interpretability for interpretability, it's also because since we have a synthesizer, since we have a knowledge domain with few parameters, we can control the sound generation process. So then we can also lead to meaningful perceptual or human understandable sound transformation. And one of the other aspect is that if you use prior knowledge, which is well chosen, then you can also learn models which have less parameters, because you rely less on learning all the models, all the knowledge from data. So then you will have models which are more frugal and which are more sustainable, and you can even gain several orders of magnitudes of in the need of data or in the need of model parameters. Okay, so then this concludes my talk, and I'm happy to answer potential questions.
Thank you very much, Gael. So questions for Professor Richard? No? If not, I can ask one question. So do you have, for instance, results on, or do you think that this can work on tasks like ASR, like hybrid approach?
So I don't work on ASR, so I cannot really answer this question. But I guess that in any case, most of the work we are doing on music or on audio are applicable on the ASR. And if I can make a parallel, is that since I mostly talk about audio synthesis, we can see that, in fact, there are a lot of work in speech synthesis. And as I mentioned also, we took quite some inspiration from the speech synthesis approach for going further with our models, which are more lean towards hybrid deep learning. But then, no, I don't have a specific answer to your question. Okay.
Any question? One question.
Thank you. One question I had about the interpretable source separation, source filter model. Did you find it is robust to various noises in the source? Because when you use this kind of models, then it can only express what that specific model can express. And sometimes when you use real world data, then there's noise, or maybe there is a source that cannot be represented as a multiple F0 salience, stuff like that.
Okay, so of course, this is a very good question. In fact, the drawback of using a model, if it's too specific, then it will not represent data which is out of the model. So here, in fact, the models is describing the mixtures as a sum of 4 sources, and the source, each of the source are built from the source filter model, where the source is a sum of harmonics and noise, and then filtered by. So then my first answer is that, in fact, we are working in extending the model to more richer mixture, because here it has been tested only on mixture of 4 singers. And its mixture of 4 singers, it's not really noisy, but the singers for one of the database, they sing together. So then there is a bit of, I mean, they don't sing completely together. They sing, you have 4 tenors and 4 bass and 4 soprano and so on, but the 4 sopranos sings together. So then you have a bit of mixtures. So there is a bit of noise, and it's still quite robust for that. And but in fact, if you add another instrument, the model, you add a 5th instrument, it will not work, because your model is exactly saying that it's 4 sources. And in fact, one of the fragility of the model, especially the one which is not completely integrated, is that you have a F0 multi-fundamental frequency estimator. And if you add noise, this will become fragile. And then you will not have the proper F0 estimator. And then if you don't have the proper F0 estimator, or you will have bad assignment to the source, then you will perturbate all the estimation of the parameters. So then there is fragility here. But the model shows also, if you do not have the proper number of sources, it still works, because if you have only one, if one source is going silent, you are going to say that one source is silent. And also the model, to defend the model, is quite a generic model because you can describe an audio source as a sum of harmonics and noise filtered by a filter. And there are many, many audio sources which can be described with such a production model. Even drum, for example, even if we have not yet result on that, but drum can be generated by a filter noise. So you just take out the harmonic or you just put a few harmonics. And so then it's true also that you are constrained by the model, but the model is quite expressive also.
All right. So I think you're right on time, so we will need to move forward. So let's thank Professor Richard one more time. And we will continue with 2 contributing talks.